I'm gonna go ahead. Okay. Welcome, everyone. It's fantastic to see such a great crowd here. We're really, really happy to be doing in-person lectures here again, and wonderful to have such a great audience. My name is Risa Wexler. I'm the director of KIPAC. KIPAC stands for a mouthful of an institute, Kavli Institute for Particle Astrophysics and Cosmology. And we're really the home for astrophysics at Stanford, and we think about everything from exoplanets to the furthest away things, 13 plus billion light years away. This is a really exciting year for KIPAC. This is actually our 20th anniversary, which is hard for me to believe. I've actually been here for 16 years. So we're planning a really exciting year of events this year, and we'll tell you more about that. And please stay tuned and join our mailing list so you can hear all about what we're doing. This has been a new experiment to have a lecture series on a specific topic, and we've been focusing on JWST, which is the newest space telescope launched on Christmas Day of 2021. It's been just a mind-blowingly spectacular success, and we were really happy to hear from two of our postdocs whose research programs is already using JWST data earlier in the year. And if you missed those lectures, you can catch them on our YouTube channel. So we heard from Ren Zeus about distant galaxies, and we heard from Simon Beer about how we use strong lenses to study the contents of the universe. And so this is the third lecture in the series. We're going to discuss how JWST is uniquely positioned to tell us more about the atmospheres of extrasolar planets. So before I introduce our speaker tonight, I want to give a big shout out to the whole team who's been supporting this lecture series. And we have a few moderators online, and these moderators are actually also subject matter experts. So I'm going to let them introduce themselves. Do I need to do something? Okay, first we have Alex. Alex, are you there? Awesome. Hi, Alex.
Hello. I'm Alex Medorowitz. I'm a 6th year graduate student and work with Bruce on the direct imaging of extrasolar planets.
Great. And next we have Arlene.
Hi, everyone. I'm Arlene Aleman. I graduated from Stanford about 2 years ago, and I've been working with Bruce, making some computer simulations about spectrographs and trying to see what information we can get out of exoplanets from those. And really excited to have everyone here.
Fantastic. And the next person is Bill.
Hey, everyone. I'm Bill Robertson. I'm a senior undergraduate here at Stanford, and I've been working with Bruce for about 3 years now, studying young systems of stars.
Great. So for those of you online, the chat moderators are moderating the YouTube live chat, which is on the right-hand side of your screen. And we welcome all kinds of questions and discussions in the YouTube chat. We ask you to be respectful to others and bring your curiosity. The moderators will try to answer many of the questions as they come in, and they'll pass the remainder to the speaker at the end of the lecture. So for the in-person people, please save your questions to the end, and we'll be taking as many as we can. Okay, so now let me go ahead and introduce our speaker. It's really a great pleasure to have Bruce Macintosh here. Bruce was, for many of the past several years, a professor of physics here at Stanford. And for the past 4 years, he was also the deputy director at KIPAC, and he was a fantastic partner in that role. This past fall, Bruce started a new role as the director of the University of California Observatory. So luckily, he has not gone very far. It's a big new job, but he's still coming to visit us very often. So Bruce's research focuses on extrasolar planets. In particular, he's interested in characterizing those planets through direct imaging. And while he was at Stanford, Bruce was the principal investigator of the Gemini Planet Imager. That's an advanced adaptive optics planet finder that was on the Gemini South Telescope and is actually now moving to the Gemini North Telescope in Hawaii. He's also worked extensively on many issues in astrophysics more broadly, including science policy. He was on the recently completed 2020 decadal survey, which sets the priorities for the entire field of astrophysics. And he's also worked very hard to make astronomy and physics more inclusive and diverse and supportive. So without further ado, let's welcome Bruce.
All right. Thank you very much. Let's see if I can make Zoom behave. Oop. And yes, also very keen on golden retrievers. So you may see the occasional dog picture as the talk goes on. Can you tell if I'm coming out on okay on Zoom? Good. Okay. I'd like to. Oh, sorry. Yes. Hide the top. Inevitable Zoom fumbling. Pardon me. All right. Better. Okay. Anyway, thank you, Risa, for the introduction, and thank you more broadly for the invitation to come back here. I was at Stanford for almost 10 years, among the best years of my professional life. KIPAC was an amazing place to be in, and it's kind of nice to be back here. And one of the things that KIPAC's outstanding about is this sort of communicating science, of giving the opportunity to talk about what we do to everybody, not just to other scientists. So I'm very happy to have this chance. And finishing this, slide advancer does not want to do. I bet I know why. There. Better. All right. And so I was invited to finish this JWST series by talking about JWST studies of other worlds, not just other planets in our solar system, but especially extrasolar planets, which is what we call, or exoplanets, which is what we call planets that orbit around other stars. And when I was a graduate student, the total number of exoplanets we knew was 0. The total number we know now is 5,000. I'll talk a little bit about what we do know about those exoplanets pre-JWST, and a lot about what we don't know about them. I'll talk then about JWST itself, and in particular, my favorite bits, which are the mirrors and the optics, because I also work on optical science, and I could fill that for a whole hour, but nobody wanted that talk. And then I'll talk about JWST's results on exoplanets, which, like a lot of JWST things, are really kind of just early teasers. The telescope was launched a little more than a year ago. It took 6 months to get it fully operational. It's made a bunch of transformative discoveries, but it's really just the start of a 20-year lifetime. And so the results I'll talk about are the beginning of what will be a transformative step into understanding the rest of the universe. And if there's time at the end, I'll even talk about what we do next, about the path to finally getting a world that's really, really, really like our own Earth. So I like exoplanets as a field for a bunch of reasons, partially because it's grappling with some of the oldest questions in not just astronomy or physics or natural philosophy, but fundamental human questions. Are there other worlds like our own? This is a quote from almost 1,000 years ago. And by worlds, Albertus, or I tend to call him Albert, was almost certainly thinking of not of planets, because he would have thought of planets as dots in the sky, but of worlds like the Earth. And that's not actually a question I can answer for you. I don't know if there are other planets like Earth's orbiting other stars, but we're close to being able to answer that. With JWST and with its successors, we know how to build instruments that can tell if there's a planet like Earth that has a rocky surface, has oceans, has a thin atmosphere, and has life on it. And I'll talk about the path that could get us there. And the fact that we are on the threshold of that sort of discovery is just one of the more amazing things in modern astrophysics. So these are the planets around the time that Albert was writing that down. As I said, he probably didn't think of the Earth as a planet. At the time, he just knew planets as little dots in the sky. They didn't really understand whether they moved around the sun or not, didn't realize that they were potentially other worlds. At the time he was writing about them, therefore, he thought there were 5 planets. There were actually 6 because he wouldn't have counted the Earth. When I was a kid, there were 9 planets, but we decided that was too many. And so now we have roughly 8 that we're aware of inside our own solar system. the familiar ones whose names you all know. Astronomers have this tendency to classify things into piles of two. If you give an astronomer sets of toys, they'll make 2 piles out of them almost instinctively. And so we classify planets in our solar systems into 2 categories. And you'll kind of do that if you look at these yourself, right? You can see there's 4 that are big. Unimaginatively, we call these giant planets. But they have some other characteristics in common. They're mostly made out of gas. What we can tell about their composition, which we can tell through the techniques I'll talk about, is 50% to 90% of their mass is hydrogen and other kinds of gases. The rest, deep in the center, we think, although we've never seen it, is a core of rock and ice that was a seed for forming the planet. And we can see traces of that seed in the planet's atmosphere, which tells us that the part about how these worlds were formed. And then the inside, the little ones, we call these terrestrial planets broadly because they're kind of like Earth. They're made out of rock and metal, silicates and iron. If they have atmospheres, which most of them do, those atmospheres are thin by comparison. The Earth's atmosphere is like the skin of an apple. It's a tiny fraction of the Earth's total mass. Very important. It keeps us all alive, but it doesn't, from any sort of geological standpoint, dominate the Earth. And they have solid surfaces you can actually stand on. With a sufficiently good spacesuit, you could survive standing on any of these planets for a moderate amount of time. And you also might, especially if you're an astronomer, classify these objects a little bit by where they are. The giant ones, all in the outside parts of the solar system, little rocky ones in the inside parts of the solar system. And when I was taught this in graduate school, I was taught that every solar system would look like this, that there was some fundamental process that made giant planets on the outside, little rocky planets on the inside. We didn't know if every star would get planets, but we thought if they did, kind of cosmic inevitability would make them look just like us. And in hindsight, that's really embarrassing, this idea that we had to be a typical universal paradigm for the way planets would form. And almost as soon as we started discovering extrasolar planets, we found out that was wrong, to the point where now I can't say how common systems like our own actually are. I can tell you how common systems incredibly different than our own are. Can't tell you about Earth's yet, but that's where we're going. And then the last thing, just a number to keep in mind on this, is how fast these planets orbit the sun, which of course they all do. How long does it take the Earth to orbit the sun? 1 year, that's why we call it a year. Planets close to the sun go faster and they have a shorter distance to go, so they take much less than a year. Planets far away take much more than a year. The fastest planet in our solar system is Mercury. It takes about 3 months to go around the sun. So substantially closer than the Earth, but not incredibly closer. Close enough, of course, that it heats up to temperatures of hundreds and hundreds of degrees. And again, the laws of nature that make that happen, pretty universal. And then I may occasionally drop as a unit, the stereotype is astronomers like to talk about billions and billions, like 93 million miles across the solar system or the 4 billion miles to Pluto or things like that. We don't, we're very lazy. And so what we actually do is we invent new units, new yardsticks, so that we don't have to remember big numbers like 93 million. And so we measure distances to planets in something we unimaginatively call an astronomical unit, which is the distance from the Earth to the sun. And so I can remember the size of our orbit in astronomical units because it's 1. That's the definition of the unit. The rest of the solar system, about 10 or 20 of these AUs. So if I accidentally say AU, that's what I mean. Okay, extrasolar planets started to be discovered right after I got out of graduate school. Initially, they were discovered not by seeing the planet, which turns out to be really hard, but by seeing the planet's gravity make the star that they were orbiting wobble around. As I said, everybody thought they would be like our solar system, which, for example, means to find Jupiter, you'd have to wait 12 years, because that's how long it would take Jupiter to go around and make the sun wobble. And so nobody almost even wanted to bother looking for them. 12 years is a very long time. But a couple of groups did. And what they discovered instead were planets that went around their star in 4 days. From the relationships I mentioned before, if it goes around in 4 days, as opposed to 3 months for Mercury, it's got to be a lot closer to its sun than to its star than Mercury is to our sun. In spite of which, the planet's size, which they could measure with this technique, was the size of Jupiter. And so instantly, the idea that every solar system would be nicely orderly like our own was completely shot to pieces. This was incredibly different than our solar system. Said, well, maybe there's one, could be weird. Nope. Almost immediately, they kept discovering them. In fact, literally, because everyone thought it would take 12 years to observe them, several people looking for planets didn't bother analyzing their data because they said, why bother until we've got years and years and years to do it. Literally the moment the first one was discovered, the next 5 followed in about a week when they looked on their desk and found, oh, well, a planet. I hadn't noticed it was in my desk. Because it was so different than everybody's expectations. We did come up with a name for them. We call them hot Jupiters because they're close to the star, so they have temperatures of thousands of degrees. They're the size of Jupiter, and they were the first extrasolar planets discovered. And at the time, it was astonishingly exciting. People eventually got Nobel Prizes for this. We had these press releases where you can see this Jupiter-like planet. I think this one's close to a binary star. It's so hot that its moon is melting. Very exciting. Of course, we don't know any of that. What we actually just knew is the star was wobbling, and so there must be a planet. We knew how big it is by how hard the star wobbles. We don't know anything else about what it was made out of. And so figuring out what planets were made out of is going to be the thrust of my talk, the ways we study the atmospheres of these planets. The way James Webb is going to mostly do that is through something called observations of transits. So here's a planet going around its star. If it happens to line up so that the planet is going to pass between us and the star will get a little bit fainter. Here's a graph of the brightness versus time. And for a little while, a few hours, as the planet blocks the star, whatever it's made out of, it's opaque, the star will get very slightly fainter. So with your eye, it'll get fainter by about 2% for a planet the size of Jupiter, but easily within the measurement capability of modern telescopes. And in fact, you can do this with a backyard telescope if you have a good backyard and the right sort of equipment. It's not even incredibly hard to measure. You do have to get incredibly lucky. Of course, if the planet's orbiting like this, don't see anything. Planets orbiting like this, don't see anything, only if it lines up right at you. So to find this, you have to look at thousands of stars. That's not actually that hard with modern gigapixel cameras, with large-scale computers. There are a lot of stars out there. Beyond that, you turn out not to need a very big telescope. And so various projects ranging from the Kepler Space Telescope, the TESS Exoplanet Survey Satellite have discovered these, but even little backyard scale telescopes. This is a survey project called WASP that basically they're almost like big home camera lenses in an array, staring at thousands of stars, and the computer looks for the one that gets a couple of % fainter for a couple of hours and says, aha, found a planet. Using these techniques, astronomers could see substantially smaller planets. Early on, of course, they just found the hot Jupiters. Those are easy because they make the star get a couple of % bigger. But with precise spacecraft, we can almost detect something the size of the Earth using this technique. And we thought, well, we'll probably find planets the size of the Earth that are where the Earth are, or maybe smaller than the Earth because there's no rocky planets bigger than the Earth in our solar system. Shockingly, they discovered again things that were nothing like our solar system, that lots of planets close to the star. And it's easier to see a planet when it's close to a star because it's more likely to line up and block the star, and because it'll block the star more often. So it's partially a biased measurement. And also all sorts of different sizes, down to the size of the Earth, but lots of things that are kind of in between the size of the Earth and the giant planets. And again, there's nothing like that in our solar system. They tended to call these super Earths because it sounds very exciting when you find something to call it a super Earth. Good PR. And NASA would have press releases where they'd say, we found a super Earth. It's orbiting in something called the habitable zone, which I'll explain later. And so maybe it's got clouds on it. For some reason, this one's kind of deserty instead of oceans. Obviously, you could wander around on it and be happy. Again, that's not what we know. What we just know is how big it is. Maybe it's a super Earth. Maybe it's a mini Neptune, which is a little bit less catchy and so never really caught on as a name for these things. So what we kind of know from these, what we don't know and what we'd like to learn. We don't really anymore have a consensus theory for how planets form. We did when I was in graduate school, made our solar system. We're still catching up with the new discoveries. Is the process that forms planets universal? Even these weird solar systems, do they all form the same way, or are there several different ways to form planets? And especially, none of them look like our solar system. Is that because solar systems like ours are hard to see, or because they're incredibly rare? Did something weird happen in our solar system? And that matters because to get, as far as we know, life, you need rocky planets with thin atmospheres, a little bit of liquid water, everything to come together. Does that happen in other solar systems, or are we relatively unique? Then can these planets potentially host life? And the big question is there actually a planet that has life on it in our immediate galactic neighborhood? And JWST looking at planets' atmospheres is not going to nail all these questions, but it can help. Looking at the composition of a planet gives you clues as to how it formed. The atmosphere of Jupiter compared to the atmosphere of Earth tells us a story about how the solar system formed. Looking at a planet and seeing a small planet, you can tell the difference if it's really a mini Neptune or a super Earth with a thin atmosphere, or if it has no atmosphere at all. In turn, that'll inform whether planet formation is a single process or lots of different ways, whether our solar system is typical, or whether it's a unique outcome. Looking at the composition of planets' atmospheres will give us a clue as to whether they could host life. And maybe it's right on the edge of JWST's capabilities. If there actually is a life-bearing planet close enough to the sun, we might be able to see hints, in particular, of oxygen in its atmosphere. Okay, now there's going to be a brief physics intro. I was a physics professor when I'm here, so I have to do a little bit of physics briefly, because I need to explain about wavelengths of light. So light, stuff you see with your eyes, to a physicist, we think of it as waves of electric and magnetic field, little pulses of strong electric fields, blip, 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 like this. The distance between two pulses of the strong magnetic field is the wavelength of the light. And different colors of light, there we go, basically correspond to different wavelengths. Blue light has an extremely short wavelength. Red light has a somewhat longer wavelength. Your eye processes this and can distinguish between different kinds of light. When you take all the colors of light mixed together to get white light, you put it through a prism and spread it out, you get short wavelengths going to long wavelengths. You can sort light into wavelengths by putting it through a prism, a process we refer to as measuring the spectrum of something. That's a handy tool because every substance in the universe has particular wavelengths of light that it likes to emit or absorb, particular wavelengths of light that it likes to interact with best. Every atom, every molecule has certain wavelengths of light it likes. If I take a cloud of gas and I heat it up, and then I pass that light through a prism, I will often discover it's only emitting a few different wavelengths, a few different colors of light that get mixed together by my eye to whatever color I think I see it, but only a few particular narrow colors are coming out of it. We refer to that as the spectrum of the object we're looking at, and it's like a chemical fingerprint. Astronomers and physicists tend to plot those spectrums as graphs, because we like graphs, a plot where the wavelength of light goes here and the intensity goes here. So each place where this bar spikes up means I have a lot of light corresponding to this color, no light corresponding to these colors, a lot of light corresponding to these colors, and so on. And I'll show some real James Webb examples of that. So these spectra are like fingerprints of different substances. If you're seeing sodium, if you have sodium gas, you'll always get these two subtly different shades of yellow mixed together and nothing else. If you have helium, if you have neon, if you have hydrogen, everything has a particular fingerprint, excuse me. You get the same thing if you have a cloud of gas that's lit up from behind, except then instead of emitting special colors, it absorbs special colors. So if I have a cloud of gas and I light it up from behind, it will absorb light. I'll get the same fingerprint, but now as little dark stripes where a little bit of extra light is absorbed at the wavelengths that atom thinks are its special friend wavelengths. And so that's the tool we can first use to study the atmospheres of planets. When a planet is doing this transit thing, when it's passing in front of the star, 98% of the light from the star just misses the planet and you see it. 1.99% of the light from the star hits the solid surface of the planet. You don't see that. A tiny fraction of the light grazes the planet and goes through its atmosphere, which means I have a cloud of cold gas, a planet's atmosphere, lit up from behind. On the way through it, it will pick up these fingerprints, these absorption signatures that will tell me what the planet's atmosphere is made out of. This was actually done before the Webb telescope was launched. The Hubble telescope has done this a lot, especially for giant planets, Jupiter-like planets, and especially for the hot Jupiters, the Jupiters that are close to their star. The one that I'll show you results from both from this and JWST is called WASP. Let me get the serial number right, 39b. We don't get to name extrasolar planets, they just have serial numbers. It's very sad. 39b. It's a hot Jupiter, so it goes around its star in 4 days, temperature of about 1,000 degrees, a little bit bigger than Jupiter, nice sun-like star. Hubble, looking at it, made a spectrum. This is the same kind of plot. It's a plot of how much light gets absorbed versus wavelength. Every bump in it corresponds to a substance. In this case, water vapor and carbon monoxide are the two main substances that are seen in the planet's atmosphere. And hydrogen doesn't show up as clearly, but is actually what most of the atmosphere is like. And, Hubble tried hard, but you can also see this is kind of ratty. These lines above the points kind of show you how uncertain they are. I'm sure you'll believe me that that bump is real, but I'm not sure about, here we go, that bump or some of these bumps. Marginal measurement, but it showed it was like Jupiter. So of course, people wanted to do this with the smaller planets, the super Earths. That gets even harder. Super Earths live here, very close to their star, that helps, but the signal from them can get swamped in the light from a giant star. And so to make it easier, we look at stars that are smaller than the sun. Stars that weigh much less than the sun also tend to be colder and smaller and redder. We call them red dwarfs. And so planets orbiting red dwarfs are not quite as lost in the glare of the star, easier to do these transit observations. And you also want planets that are orbiting close, because even with Hubble, one pass in front of the star was not enough to get a good measurement. You have to watch it go in front of the star again and again and again and add up the signal. If it takes 10 years for it to go around the star like Jupiter, getting 10 measurements of that would take a really long time compared to a PhD thesis. So it's much better if it'll go around the star, say, every 4 days. You can observe it again and again and again. And so the planets that are easy to do are these close-in ones. One of the early super Earths that was observed has the serial number GJ, which stands for Gliese for some reason, 1214b, period of really short, 1.5 days. It's a super Earth, about 2.5 times the size of the Earth. It's really close to its star, but its star is also pretty faint, so it's only a temperature of 200 degrees Celsius, 300 or 400 Fahrenheit. Super Earth, mini Neptune, water world, that's what they wanted to measure. With Hubble, they didn't really get an answer. The colored lines are what the spectrum should have looked like if the atmosphere was made out of water, out of methane, out of carbon dioxide. What they got are these circles with error bars around them, flat as a pancake. There was no evidence of absorption in the planet's atmosphere. Could mean it doesn't have an atmosphere. We don't think that's the case. Instead, what we think it means is its atmosphere was dominated by things that absorb light uniformly, like clouds. Clouds of cloud particles would pretty much absorb all the visible light. That's what clouds do. You'd see this flat, boring spectrum. You wouldn't be able to see deep into the planet's atmosphere. So how do we do better? A little bit more physics. Visible light, of course, is just a tiny fraction of all the kinds of radiation there are out there. A really tiny fraction. Much shorter wavelengths of light are things like ultraviolet or X-ray radiation, and there's whole other talks on what you can do with telescopes that look at those. Much longer electromagnetic radiation are what we call radio waves. They have wavelengths of meters or centimeters. You can actually practically see them. You can pick them up if you have radio hands. In between, longer than red radiation is what we call infrared radiation, and that's what the James Webb Telescope was designed to look at. Infrared radiation, wavelengths all the way from about 1 millimeter to 10 to the minus 6 meters, a micron, 1,000th of a millimeter. This is actually my dog with an infrared camera. It has two interesting features. One that we're all used to is it's the kind of radiation that objects emit when they're sort of room temperature. All of our bodies are emitting infrared radiation right now. How much radiation you emit is actually related to the temperature. If you look at the dog, where her mouth is open, you're seeing her warm tongue. The rest of her body, you're seeing the surface of her fur, which is a little bit cooler. Or if you can squint, it's kind of hidden by the logo from the camera, but the little nose is darker because it's an adorable little cold dog nose. So you can learn properties of objects by the infrared radiation that it emits. Pretty cool. Another feature that's very handy and less appreciated, any kind of radiation can kind of sneak around objects that are smaller than its wavelength. For visible light, that doesn't help much because nothing's really smaller than visible light most of the time. Infrared radiation, long infrared radiation has a wavelength of 1 millimeter, which means it can go through things that are thinner than 1 millimeter, which includes your clothes. And in fact, the airport body scanners you stand in are not X-ray machines. They're infrared cameras that use a long infrared wavelength that your clothes are transparent to. Your body thicker than a millimeter is not transparent to them, and so they can see your body but not your clothes. Similarly, those clouds, those irritating clouds I mentioned, have particles that are kind of a micron or so, and so if I look in the infrared, I could see through the clouds partially and see what's going on in the planet's atmosphere. So the James Webb Telescope was designed to do that. Let me see if I can get the video to play. There we go. Won't go through all the steps of deploying it. It was like the most stressful month in all of astronomers' lives. It was 2 million kilometers away from the Earth, and it had to unfold itself completely automatically. All the different parts had to come out. I'll talk about those parts in later slides. I tried to ignore it and sleep, but I have colleagues who worked on it, and it worked. All of the motions came, all the bits came down when they're supposed to, and over the course of a month, it deployed itself. What I'm going to talk about, though, is the next step. So you can see the mirror is made up of these 36 individual pieces. That's so it could fold up and fit in the rocket. Also, so the pieces could be very lightweight, and also to give us some ability to adjust the mirror. The Hubble Space Telescope, we made the mirror on the ground, launched into space, and found out after we launched it into space, we'd made it the wrong shape. No one ever wanted to do that again, so the Webb Telescope mirror pieces can all move so that we can adjust its shape in space, even if we didn't get it quite right. So here's a picture, pre-launch of all the segments. They all have numbers. Here's what they look like in a cartoon, and here's them from the side. I have a personal favorite segment. It's segment A6 up there. It's the best segment. We'll try to keep an eye on it as we go through this. The segments are supported from behind with motors so that you can move them. You can tip them, you can tilt them, you can push them, you can rotate them, and you can even bend them if they turn out to be slightly the wrong shape after launch. When they were launched, all the segments were pressed up against their supports to hold them perfectly still so they could survive launch. After that, they were all pushed up by about a centimeter. That's how far away from their supports go, except for A6, which was slightly slow, poor thing. It's part of why I bonded with it. It took it a while to get to its final position. But they did all move them into their final positions, but not perfect, because you can't make something perfect and have it survive a rocket launch perfectly. To start with, they looked at a bright star and tried to see where each segment's image of the star was going when they weren't all aligned. And they got something like this. Every segment makes its own little copy of a star. You're getting 18 different copies of the star spread out. They then moved each segment so they could figure out which copy was which, and aligned all 18 of them into a nice regular grid, not pointed in the same direction, but all under control so they know where they are. And some of them, like A6, made pretty good images. Some of them made pretty lousy images, indicating that the segments were not yet the right shape. And so the next step was to adjust all of these segments, to rotate them, to pull them, and to push them until they're the right curvature, and to sharpen up the images, as this video is showing. That took about a month, one segment at a time, exquisitely carefully, but they got them all to be perfect. Then they aligned them all so they combine into a single star. A little bit more trickery, we got the first JWST images, the sharpest image of a star ever made in the infrared in space. And they were just looking at a star. It turns out there's these damn galaxies all over the place. It was just littered with galaxies that my colleagues told you about in the previous couple of talks. Also has a selfie mode where it can take pictures of itself to make sure that the segments are all okay. So given that, why is it good at exoplanet things? One, it's just big. It's bigger than any space telescope we've ever launched, bigger than any infrared telescope. Get a lot of light, planets are faint. Two, it's cold, which is important for infrared. This thing on the bottom is a sun shield that protects it from the sun, so the whole telescope cools down to the temperature of space, because warm things give off infrared radiation. You don't want it to swamp the ability to see planets, so we cool the telescope down. And the third feature, which is actually the most important for exoplanets, is it's really stable. The Hubble Space Telescope orbits the Earth in low Earth orbit, goes around every 90 minutes. And while it's doing that, it goes in and out of the Earth's shadow every 90 minutes, which if you're a telescope is like getting hit on the head with a hammer every 90 minutes. The Hubble telescope goes proing every 90 minutes. Webb is 2 million kilometers away from the Earth, and it always orbits to point its sun shield at, spoiler in the name, the sun. So its temperature never changes. The telescope just sits there quietly soaking into space, and it's exquisitely stable, which if you want to see a tiny signal from a star as a planet goes in front of it, turns out to be really important. So Early results, which is all we have to talk about so far, demonstrations, it looked at that same WASP-39 planet. This is kind of an example of a transiting planet. This is the discovery of WASP-39. This is the change in brightness of the star. And here, the star is just changing in brightness because we're looking at it with a telescope on the ground. The atmosphere is in the way. Birds are flying over. The telescope's not perfectly stable. You can see a signal where the transit happens, but you kind of have to have a little bit of faith that that's really what's going on. This is the Webb data, zoomed in even more. You can barely see that there's any noise in that data. And in fact, that noise is not even the telescope's fault. That's probably mostly the star is not staying perfectly stable, even when the planet isn't in front of it. So it's just a beautiful light curve, we call it, exquisitely precise. This was an easy one, size of Jupiter, but it says Webb could see something much smaller than Jupiter easily. And all that light got fed into infrared spectrographs. Again, could spend hours talking about every detail of these. Webb has multiple spectrographs looking at different wavelengths of light. We can see features, for example, from water in the planet's atmosphere. It doesn't mean liquid water. It's got a temperature of 900 degrees. It means water vapor, but it's there. Carbon monoxide, carbon dioxide, which we knew was supposed to be there, but is really hard to see from the Earth because there's all this carbon dioxide in the atmosphere. And so it was the first really clean detection. And my personal favorite, sulfur dioxide, which is not something anyone had seen or even expected to see. Sulfur dioxide actually shouldn't exist in a planet at this particular temperature. But what it is smog. That's a big component of smog if you're in Los Angeles, Mexico City, somewhere with significant smog. Molecules get broken up by sunlight and recombine to make more complicated and unpleasant molecules. The same thing is happening in the planet. Its chemistry is being changed by going next to this star. So we're not just doing astrophysics, we're doing astrochemistry with the James Webb Space Telescope. We can trace the flow of every substance in its atmosphere. I'll talk quickly about the other way we look at planets, which is called direct imaging. So that's actually what I do. And again, a whole other talk, which you can find on YouTube. We do this with ground-based telescopes. Webb is going to be really good at it. Direct imaging is when you actually say, I'm tired of seeing wiggles on graphs. I want to actually see a planet next to a star. The problem is planets are really faint. Stars are really, really, really bright. It's like you're looking at a lighthouse and you're trying to see a firefly next to it. Jupiter in our solar system is about 1 billion times fainter than the sun. Really hard to see when it's right next to the sun. You could imagine pointing Webb at a really bright star, which they did, and overexposing it to see if you see any planets, which they didn't do because they knew they wouldn't. If you did, you'd see good but not perfect telescopes. So there's kind of like lens flare from the telescope. That is about 10,000 times fainter than the star, incredibly brighter than still Jupiter would be. You'd never see Jupiter in this mess. And so we cheat a little, and we look for planets that are a little warmer than Jupiter, taking advantage of the fact that warm things give off infrared radiation. How do you make a planet warm? You could make it warm by putting it close to its star, but then it would be too close to the star to see. Instead, we look at planets when they're young. It turns out when you form a planet, you release a lot of energy, and it just takes a while to cool off, like you took it out of the planet-forming oven, and it's just sitting there for a while. If you catch it within a few minutes of leaving the oven, or a few million years, it'll still be warm enough that you can see it in the infrared. That lets you see planets way out at the outer parts of solar system that will never transit their star. Again, they picked one they already knew about. Its serial number is HIP 65426b. It was discovered by a ground-based telescope run by my arch rivals. It's again sort of Jupiter-sized, warm because it's fresh out of the oven, a temperature of about 2,000 degrees. Nobody really knew how heavy it was or what its temperature was. Webb can't see it directly. These are images when you point at the star, still don't see any planets. But you can do one last trick, which is look at the star with the planet, look at a star without the planet, and look for a dot that moves, that isn't the same in the two images. And when you do that, you get these beautiful detections of this planet at a whole bunch of different wavelengths. It's a nice paper by Aaron Carter, who's a postdoc now at UC Santa Cruz. And they looked at it at a lot of wavelengths. And those in turn tell us a lot about its composition. Hydrogen, water, carbon monoxide, they tell us its mass, they tell us its temperature. They actually tell us we got the temperature wrong with our ground-based telescopes because we couldn't see all the infrared radiation. They're the sort of first hint of how to study these objects. This is a spectrum of a slightly different one, a paper by Brittany Miles, who just finished her PhD at Santa Cruz, now at Harvard. She's really brilliant. We can see substances like potassium and sodium. We can even see these irritating clouds and see what they're made out of. And they turn out to be made not out of water vapor, way too hot for that. They're made out of silicon. They're clouds of vaporized sand particles, basically, dust, clouds of dust. Going beyond that, we'd like to end up moving towards studying Earth-like planets. So I kind of promised you we'd get to Earth-like planets. Not there yet. We've only had the thing in space for 6 months, but at least there's a path to get there. So I have to introduce one more concept, which is the habitable zone. You might have heard before. The Earth is habitable because we have the right temperature for liquid water on the surface. And that's because we're not too far from the sun, not too close from the sun. Mars, too far, freezing cold. Venus, too close, blasting hot. We're kind of just right. So we refer to this sometimes as being the Goldilocks zone, the place where planets could potentially be habitable. Also, the only place in the solar system where you will find bears, so it's fairly appropriate to refer to it as the Goldilocks zone. In our solar system, that's out where it takes a year to go around the star, which is a terrible place for transits. JWST can only see planets really close to their star using transits, long way away from the Earth. But if our star were smaller, that Goldilocks zone would be much closer to the star. If you're orbiting a really small star, you have to huddle up close to it for warmth to even have a chance of having liquid water on your surface, right where JWST would want you to see it. Not even a medium-sized star, but a really small, really red star, the JWST sensitive zone will hit the habitable zone and you'll be able to see planets. So we wanted to look even before JWST was launched for systems like that, for really small stars that had planets orbiting close enough to them that they're in the habitable zone, that were Earth-sized, that we could do transits. Some people thought it'd be really convenient if you could find a system with lots of planets like that all at once, packed in close together in the habitable zone, so you could measure several of them with a single observation of the telescope. Other people said, that's crazy, you'll never get that lucky. But actually a group did. They discovered a system called Trappist-1. It has 7 basically Earth-sized planets in it, all of them packed closer to their star than the orbit of Mercury, huddled around this incredibly low mass star, so that 3 of them are sitting in this Goldilocks zone where they might have the right temperature to be Earth-like. We don't know, of course. The NASA press release says, ooh, some of them are like Earth's. Right now, we just know what size they are, but Webb is going to look at them. This is like the #1 long-term exoplanet target. My friend and colleague Nicole Lewis at Cornell is part of multiple teams are going to lead observations of these planets. And they might see something like this. This is a simulated spectrum. You don't get to see a real one yet, but carbon dioxide, water vapor, the 2 colors are 2 different planetary atmospheres, but even a tiny hint over here of ozone, a signature of oxygen on the presence of the planet. The tricky bit is that will take at least 50 transits worth of measurements added together. Even though you can get one every 4 days, people keep wanting to borrow the telescope and look at galaxies and stuff like that. So this is going to take a couple of years of Webb observations to reach the final point where we have them. But it's a thing Webb can do. I wouldn't bet that we're going to get an Earth on it. I'm actually I'm not pessimistic, but I think the universe is different than we can imagine, and we're not going to get an Earth-like planet, but it's possible. In the near future, I just wanted to show this graph because last week proposals were due to use the James Webb Telescope, every astronomer in the world competing for it. This is a graph of the number of proposals that were submitted last week as a function of time, approaching the deadline, which was 5 p.m. Friday. I need to change the axes on the graph. Let's see if there we go. In the end, there were astronomers also procrastinate, so a lot of them were finishing on Friday. 1,600 proposals, about 7 times as many as there is time to observe with the telescope. So what it's going to do, I can't actually tell you until the committee meets and sorts all of this out. I have a few more minutes. Let's say a little bit about the very far future. So Webb could see oxygen signatures around a planet close to a low mass star, but there's only a few stars like planets like that that we know of, and maybe tiny little low mass stars don't get to have planets like Earth on them. They're very different than our sun. If we want to probe the transit zone close to the star, if we want to probe the habitable zone around stars like the sun, we are going to need something different. To do that, we won't use transits because 50 transits where you get 1 a year, long time to get a measurement, we'll have to use this trick of imaging. We'll have to block the star and look for the planet. Webb can't do that at the level of sensitivity we need. An Earth-like planet is about 1,000,000 times fainter than the planets it's already looked at and much, much closer. And so astronomers are thinking, as we always do, about what to do next. And there are concepts out there for the telescope that will launch after Webb that will use the same technology, but incorporate much better hardware for blocking the star and go back to visible light. Because if you want to look at a planet like Earth, visible light is actually pretty good. Our atmosphere, it turns out, is really transparent to visible light, as you'll notice if you go outside after this talk and look at the stars. And visible light lets you make sharper images and see planets more clearly. And so we've decided the next thing to do will be a roughly Webb-sized telescope, but optimized for visible light and even more stable. Webb is stable with all those sun shields. Its mirror moves by less than, I try to get this in units of a human hair. I think about 100th of a human hair is how much the Webb mirrors move. The 100th of the thickness of a human hair is how much the Webb mirrors move, which is amazing. To see an Earth, you have to be about 1,000 times better than that. You have to move by less than an atom over the course of a week. We think we know how to build a telescope like that, but we've got to design it from the ground up to do it. These are concepts for it. It's now called the Habitable Worlds Observatory, which is a pretty cool name. And if we decide to move forward with it, it's the next big thing that we could potentially do in astronomy. And it could make images like this. This is our solar system like our own seen from outside, with planets like Jupiter, planets like Neptune, but one planet here where finally the spectrum shows a signature from oxygen. And a telescope like that could look at about 200 stars like the sun. And if there were Earths there, it would be able to see oxygen around them. And so that's actually what we'll do next. But in between now and then, we get 20 years of really awesome James Webb results. And let me stop there.
All right, thank you, Bruce. That was great, exciting present and future. Okay, so we're gonna take questions now, or we're gonna alternate between questions online and in the room. Let me in the room especially encourage questions from younger folks, but everyone is welcome. Okay, go ahead.
Question. So you say it's like 15 times different observations you have signals uploading at time. Like, how do you count for
So one question was like, if I have to combine 50 measurements of the planet to get a good signal, how can I account for stability of the planet you're looking at? And to some extent, you just have to hope that it's stable, that it will stay the same. And the things we're trying to measure mostly will, like the fraction of oxygen in the Earth's atmosphere doesn't change over the course of a year. Fraction of CO2 in our atmosphere is changing, but even that takes about 100 years to change. So you could potentially notice that it's changing by comparing the start to the end, but mostly I think we'll hope that the planet is stable. And that might be a problem. Maybe there are huge storms and the whole planet gets cloudy for a week. That's something we're gonna have to find out. But we'll hope that the bulk composition of the planet's atmosphere doesn't change too much.
All right, let's take one from online. I have a question from Shreya who asks, how big does a star have to be to have planets orbiting it?
The Trappist one is actually one of the very smallest stars known. It is basically a little bit bigger in radius than Jupiter. Its mass is about 80 times the mass of Jupiter. It's literally as small as we think you could be and still count as a star. And not only does it have planets, it has 7 of them. So we think pretty much every star down to the very smallest is likely to have planets.
All right, one in the room.
So it's going to be 2 years before we get data on TRAPPIST-1 that would
Maybe 1 year. I shouldn't be too pessimistic. Yeah.
Evaluate a biosignature. Is that the earliest? And then, and what about the other candidates? How much longer will it take before you could evaluate biosignatures on exoplanets?
I believe they're going to do most of the Trappist planets over kind of the next year. And then I was adding an extra year to allow time to analyze the data, and you want to be really sure before you call the New York Times with a biosignature or something like that. So we should get the first flurry of Trappist results. Almost certainly they'll do teasers. They'll say, oh yeah, we saw water. Water's easy. And then go into more depth as it goes on. So it actually probably will be kind of a series of incremental results. Other ones, there's only about 2 to 4 really good Earth-sized planets in the Goldilocks zone around low mass stars that Webb can do. And so they're doing the Trappist ones first. They'll do the next couple over the next couple of years after it. We might discover more, but they'll probably have gone about as deep as you can into this over sort of 4 to 5 years. But depends a little bit on the prioritization of those 1,600 individual proposals that I mentioned.
All right, we have a question over there.
Almost certainly, now that we've shown that it worked, that building the mirror out of pieces like that and aligning them, everybody was terrified that we wouldn't be able to line them up or the segments would fall off and stuff like that. That actually I had faith in, because I know the people who are doing the optics and they're really good. It worked. So almost certainly that's how we're going to build our telescopes in the future. Instead of one big, huge piece of glass, we'll have pieces and we'll move them and we'll adjust them. We'll keep using that technology. We'll make it better. But now that we've done it, we're going to keep doing it. That's a really good question.
Great. Okay, let's take another one from online. We have a question from Gabe who asks, how does the formation of terrestrial planets influence where they are and their characteristics within a star system?
That's a long question to answer, but one example would be when a planet forms, does it suck in a lot of the hydrogen gas that's there when it's forming? So we think the planet's formed in a disk of gas and dust. Little rocky dust particles turn into the cores of the planets. Jupiter got big enough that its gravity then sucked in the gas from this disk and made a huge atmosphere of hydrogen that you can't live on. Earth, we think, formed so slowly it didn't form and it didn't suck in any of that hydrogen. The atmosphere we're all breathing right now actually was released from the Earth after it formed. It comes up from our atmosphere, pretty much all comes up from volcanoes and things like that. So we think, as an example, if planets form slowly, then they don't get covered with hydrogen and maybe you can live on them. If on the other hand, super Earth planets form really quickly, they probably do suck up a little bit of hydrogen. And so they would have atmospheres that are not really potentially life-bearing atmospheres.
All right, so many questions. I'm going to take one from way in the back there. Yeah, yes, you. If you can repeat the question.
The question is sort of what are the bottlenecks in getting observations? It's really the time to make the measurements. It takes hours and hours and hours to make measurements, and there are lots of different measurements people want to make with it. Staring at faint galaxies, looking at planets. In the case of the transits, the other limitation, of course, is you have to wait until it ticks in front of the star. So you get a couple of hours every 4 days. Takes a long time to build up measurement after measurement. Sending data back to the Earth is actually not that hard. It takes large amounts of data, but not gigabit Ethernet quantities of data. So zooming the data back to Earth for Webb is fairly straightforward. It's really just there's so much to do, and these stars are faint, and these measurements take a long time.
All right, way in the back over there.
The question was that these exoplanets are moving very fast. Can Webb do things like measure changes in their shape or evidence of planets degrading? In principle, people are looking at that a little bit for some of the giant planets. There's some evidence that they have like trails of gas coming off them, that they're so close to their star, they're getting eroded. You probably wouldn't see them change shape over a few years because these planets are millions of years old. They're not going to disappear by next Tuesday. But people are going to look for things like that. And there's a whole other talk I didn't give about trying to look for whether one side of the planet is brighter than the other, whether there's evidence of weather. That might actually be within Webb's ability to see for the giant planets, that sometimes it's brighter on the left, sometimes it's brighter on the right. So we might be able to see not planets disintegrating, but we might see them changing. We might actually make measurements of weather going forward.
Right.
When you talk about the Goldilocks zone, do you think we're taking a too biased view of what constitutes a life form?
Yeah, the question is this Goldilocks zone too biased and Earth-centric? And we do have that tendency, like I alluded to about other solar systems. There's a little bit, though, of the old joke about you lose your keys and you're looking for your keys underneath the street light, and someone says, is that where you lost your keys? You say, no, I lost them over there, but it's too dark, so I'm looking where the street light is. If there were other kinds of life, they'd be really hard to see with telescopes, most of the kinds that we can think of. So we're designing experiments that will look for life like us. If we see something strange that we can't explain, we will almost certainly try to think of whether there's a life explanation for it. So I tend to hope that we're designing experiments that are flexible enough that they could see other signatures. But, for example, in our solar system, there might be life under the ice of Europa or Enceladus, these ice moons in the outer solar system, heated from beneath. There might be oceans that there's life in. I can't think of any way I could see that from 100 light years away. I can't even tell for sure if that's happening around Jupiter, and you can practically drive to Jupiter if you have a fast car. So to some extent, we're looking where the streetlights are, but we know it operated as a procedure once. But just as the last thing, that's part of why what I'm really motivated by is, maybe we get lucky and find the oxygen, just to say why I do this. But even if we don't, understanding how planets form and evolve will help tell us if maybe there are pathways to other life that someone smarter than us can think of studying those systems 50 or 100 years from now. So understanding the variety of planets. And I have a closing line on that, but I'll save it maybe till we do a couple more questions.
So we have a question from online from Tom. So how far away can we see exoplanets with current technology?
Depends a little on how much detail you want to see. So we can count exoplanets with a mission like Kepler to thousands of light years away. But that's so far away that even with Webb, you can't really get a lot of details of their spectrum. With Webb, you can get good spectra to a couple of hundred light years away. And not most planets, because they still have to line up just right. So Webb is probably only seeing a tiny fraction of the planet, and Kepler and all these missions are only seeing a tiny fraction of the planets that are out there.
All right, yeah.
How many people are manning this right now? And how do you account for potential debris that might hit it?
The question was, how many people are manning it, and do we worry about debris that might hit it and stuff like that? I think there's like 5 people on duty at a given time. I'm not 100% sure how big the staff is. There's a large institute that runs it and people do shifts and stuff like that. The good news is debris, like man-made junk, is not going to hit it because it's 2 million kilometers away. We have littered Earth orbit with crap, but it's far enough away that it's not at an immediate risk of running into any human-made junk. The bad news is it got hit by a meteor already. Tiny meteor, micrometeor. It did knock the segment enough that they could tell, which is mostly a measurement of how accurately we can measure the positions of the segments, and they brought it back into alignment. And it wasn't A6, so I was reasonably happy about it. But it's definitely an issue. And in fact, they're now going to point it downwind. They're basically going to point it backwards as it moves through the solar system to slightly reduce the chance of a meteor smacking into the front surface. Hopefully, it was just one unlucky one, but it was bigger than anyone expected. Bigger, of course, is like that, but it was a little disturbing.
All right, question there.
Does the Webb system have the ability to detect tidally locked planets? And is that something even of interest?
Almost all the so the question is, do we have the ability to detect tidally locked planets? What, you might ask, is a tidally locked planet? When you're really close to the star's gravity locks the planet. So like the moon always keeps the same side facing towards the Earth. Planets close to their star will always keep the same side facing towards the star. And in fact, every planet I showed you a result for is almost certainly tidally locked. They're so close to their star. So everything we look at will be like that, which might be another reason why life on them wouldn't be like life on the Earth. They're not going to have day and night and the kind of simple cycles and rhythms we have here. It's another reason why it'd be nice to build the next telescope where we can get away from the tidally locked ones and see more ordinary planets.
All right, we have a last question online. We have a question from Eric who says, the JWST mirrors are very cold. How do they work at such cold temperatures? And do the movement motors require lubrication?
Yeah. So the mirrors themselves were designed to be good at cold temperatures. And in fact, they're made not out of glass like ordinary mirrors, but out of metal, out of beryllium, which is really lightweight, which is great, incredibly poisonous, which is part of why it took a long time to manufacture them. But because they're metal, they hold their shape when they're cold. You wouldn't want to lick them, A, because poisonous, B, because they're really cold and your tongue would freeze to them. But they stay very uniform even when you make them cold. They don't get brittle or break or anything like that. The motors don't have lubricants in them. They're just really, really, really cleverly designed so that they can keep operating even without lubricants and make these tiny motions.
All right, I have been told that for the sake of time, we need to not take any more questions. I know there's a ton more questions in the room, but Bruce is going to stick around, and feel free to come down and ask your question. Before we wrap up, I'm going to just introduce a couple more ways you can learn more about what we're doing at KIPAC. And let's see. Are you showing something?
Stop sharing.
Okay, first on the KIPAC website, which is easy to remember, it's kipac.stanford.edu. We have a whole list of outreach events, and I encourage you to take a look. We try to talk to the public in lots of different ways. Actually, the next opportunity to hear one of us talk is going to be me. I'm giving a talk at Cal Academy a week from today. So that's in San Francisco. If any of you want to come up to San Francisco and check out the planetarium, I'm going to be talking about the dark universe, tiny galaxies, the largest maps of the universe that we make. We're going to have a special event on March 7th. We're going to host a Spanish-only public lecture with sort of 3 mini talks on galaxies and cosmology, including a Q&A. And then I mentioned at the beginning that this year is our 20th anniversary. So on April 15th, we're going to be having a big open house event here on campus. It will include some mini lectures, but it will also include a lot of hands-on activities. And it should be a lot of fun. It should be very family friendly. So please feel free to bring your kids and your grandparents and everyone in between, your dogs too. It will be outside. Some events will be outside. So anyways, it's been just a real pleasure to have such a fantastic audience. Let's thank Bruce again. And please feel free to ask Bruce more questions, and I hope to see you at our next event.